far the contribution from the saturated areas. So let's suppose that we have these saturated areas around the river network, and we have computed the contribution of this saturated area to the surface runoff. But these contributions are spatially distributed. And instead, what I'm measuring, what I'm observing is the discharge here. This is QT. And so they thought that we need to introduce a component of the model, a module, to transfer the contributions to the basin outlet. And the idea is to get into iMod two separate transfers, a quick transfer, or also it's called quick routing, and a slow routing, in order to take into account that part of the transfer takes place into the rivers, so it's indeed something that is very fast, and part of the transfer takes place over the hill slopes, so it's slower. So once that we computed the total contribution to ER1 and ER2, the idea is to split this contribution in two components. One component is obtained by multiplying the contribution by a weight that is indicated with the value, with the symbol alpha, 0, which is comprised between 0 and 1. It is in the range 0, 1. And the other contribution is, sorry, 1 minus alpha. And these two contributions are routed, transferred to the outlet, to the closure of the catchment, by using, in one case, a linear reservoir, so this contribution goes into a linear reservoir, which is characterized by a time constant, which, let me see the symbols here, is Ks. The other contribution goes into a sequence of 3 linear reservoirs. And finally, gets to the closure of the catchment. So 1, 2, 3 linear reservoirs. And the constant is the same for all of them. And the constant is Kq. And the scheme is depicted here. Now, let's focus first of all on this. So, as I said, you have ER1 plus ER2. This is a scheme that was taken by the original paper, which is not a paper, it's a PhD thesis, proposing this model. So basically you have ER1 plus ER2, you have the alpha separating them, and then you have a linear reservoir for computing the fast runoff, and a sequence of 3 linear reservoirs for computing the slow runoff. So basically, you don't have to be concerned by the complication, because applying a linear reservoir or a sequence of linear reservoirs is just a matter of one equation. It's very simple. And so this is what you get. And this is this part on the right of my arm is what is we are discussing now. Now let's look at the whole picture. The whole picture represents indeed how the model works. And basically this graph that you see here is what I depicted in my lecture and on the blackboard, with the only difference that this graph is oriented in a way that doesn't help to understand how the model works. Because basically we have f from 0 to 1 in this horizontal axis, and you know it goes from 0 to the right to 1 to the left. So basically this graph is the same that I developed on the blackboard, and it's the same that I proposed to you in my lectures. I need to correct it now. But it's rotated. It's rotated 90 degrees on the left, anti-clockwise. So, but it's the same graph. And you see that in the same graph, you can recognize that it's the same graph because this is the curve FC. You see that F is here and the storage is here, between 0 and Cmax. So the area below the curve is ER2. And the area above the curve is W. So it's saying the same thing, but it's rotated, so it doesn't help much. And also it depicts that you have rainfall falling here and evapotranspiration going out. So what is the reason why the author wanted to basically depict the scheme in this way, with this orientation? Because it helps in seeing I model as a reservoir model with an upper value of the storage that is varying. So if you look at the storage is not the same over the whole catchment like you have here. You see, these are tanks with the maximum allowed storage that is constant. In this case, he had the idea of representing the model like a tank with a maximum value of the storage, but the actual storage is varying over the basin. So he wanted to depict it like a tank with an upper border that is not horizontal, but it's shaped. And so you can see that the water rainfall that falls into the tank and remains under the curve is storage in the tank. What it goes above the curve cannot be contained into the tank, and therefore it's surface runoff. So this is why he had this idea of rotating the figure, because he wanted to show that it's like a tank with a variable upper value of storage. I don't think it is really helpful in understanding. For students, I think I always found it difficult to explain this. So this is why I wanted to adopt a different approach. And I think that once that I corrected the figure, it's probably more easily understandable. But this is something more from the conceptual point of view, probably is something that is more visible. Okay. And that's it, finally. But let me make a summary of the number of parameters and the parameters. So how many parameters does IMOD count? I said 2 up to the introduction of this scheme. So now we have to, besides Cmax and beta K, we have to take into account these additional parameters. What are the additional parameters? Alpha, to be calibrated, and KQ and KS, the two constants. So at the end of the story, IMOD counts 5 parameters. The reason why I wanted to introduce this model to you is that I still believe that this model is simple, because if you look at the number of parameters and the code, you will see that the code is really very simple, it runs very fast, and this is a model that can be really applied in practice. I applied this model to several consultancy activities that I made recently when I had to set up a mathematical model for the rainfall runoff transformation that is a bit flexible and therefore, I mean, easy to apply. I recently used only IMOD, because the linear reservoir is really something that it's not enough, it's not flexible enough, and so sometimes it's difficult to adapt to get good simulations. With IMOD, indeed, the performances are fine, and IMOD was proposed in 2000, so it's a relatively recent model, and the first systematic applications are about 10 years old. There are a lot of similar models like IMOD, a lot. There are many of them, and the literature proposes many of them, and you may find also on the web the codes available. And two alternative popular models, I just want to mention them to you, because you can find on the web the codes. One is HBV. HBV counts up to a maximum of 11 parameters. And HBV, you can find an R code for applying it. And another very popular model is SWAT. And the SWAT has a module also for simulating water quality, and therefore is particularly used for agriculture applications, where they also need to take into account the impact of fertilizers on water quality. I don't remember the number of parameters of SWAT. I think it's about, it depends on the type of simulation that you carry out, but it should be around 10-15. And for both SWAT and HBV, you can find the codes. HBV in R, SWAT has its own code, and it's not easy to apply. I applied sometimes HBV, because with 11 parameters, of course, you get more flexibility, even more than IMOD. But still, I think IMOD is the best compromise between understandability of its structure, number of parameters, and easy application, because it's, as we will see starting from tomorrow, it's easy to apply, and it is very fast. Okay, let's make a break.